Okay, now as I just said, it's important to understand these arguments so you can make similar arguments in other situations. These are just foundational arguments. All kinds of situations where you need to make arguments. And of course I can't catalog those for you right now. I do want to talk about potential differences, okay? For this field, the potential difference between and I said distance A to distance B, I want to change that because I don't want to have to replace A. I'm going to call it R1 to R2. Okay? Is what? It's delta W from R1 to R2 divided by Q. In other words, the work done on charge Q from position R1 to R2, right? And it's negative the work done on the charge, because that's the definition of potential energy change, right? Equal and opposite to the work done by the conservative field, okay? And what's the work done between here? It's the integral from R1 to R2 of Q E dr over Q, which is then negative integral from R1 to R2 of E, which is 2 pi 2K, not 2 pi, and instead of using A, I'm going to use R here. I still am glad I used R1 and R2 because A would have been confusing. Okay. Equals this, right? And that integral is real easy to do. You get 2 pi K. And you should be able to do this integral. You shouldn't have to memorize this formula. Okay? You should understand this and be able to do this integral. Well, it's going to be that times the natural log of what? Well, the integral dr over r is the natural log of r, right? Okay, evaluated from R1 to R2, it's the natural log of R2 minus the natural log of R1, which is the natural log of R2 over R1, which is the negative of that. Okay? So it's the natural log of R1 over R2. Now we want to check that out, and I want to check that out against intuition. Okay? If you have a positive line charge, then the field is in this direction. Okay? Meaning, it's analogous to having a gravitational field in this direction, right? If you move parallel to the gravitational field, your potential energy goes down, right? Okay? So if you have a positive line charge, that is and it's, I keep wanting to write pi in there. It's 2 lambda times k, not pi times k, right? There's no pi in this thing. Okay? 2 lambda k is going to be positive, right? Which means that you better get a negative here if you're moving from a smaller, if R1 is less than R2. If R1 is less than R2, you're moving in the direction of the field, which is going to decrease your potential energy. Okay? Because the field is doing positive work on you, and the change of potential energy is equal and opposite to that. You have to have that whole concept, which I've been nagging you about since October, early October. Okay, now, definition of potential energy change, okay? So, you have 2 lambda k times natural log of R1 over R2, right? If R1 is less than R2, this should be negative then, assuming lambda is positive, okay? Well, is the natural log of R1 over R2 negative if R1 is less than R2? Well, yeah, natural log of any number between 0 and 1 is negative. If you understand the natural log function and can visualize its graph, you can see that immediately. Okay, but if you understand it as the power to which you have to raise e to get the number, you have to raise e to a negative number to get a number less than 1. Now, I just said that, okay? Anybody who's actually watching this has to sort through what I just said, but I'm pretty sure it's all correct. I didn't write it down, though, so, you know, I don't care what your transcript says. Whatever I said is right. Okay, no, pretty sure I had that right because I was actually careful when I did all that. If I happen to get it wrong, you still understand from what I said how to reason it out. But that checks out. Okay? Once I got all my symbols right, which is always a challenge. Okay. So that's potential difference. Wherever you are in the vicinity of this line charge, if you go from this distance to this distance, change in potential, change in voltage, change in electrostatic potential is 2 lambda k times this natural log of this ratio. It comes directly from this and from the work integral. Okay? And it doesn't matter whether you go directly away from the wire from this distance to this distance, or go from here to some point 10,000 miles out that way at the other distance. Why is that? Because this field is conservative, it's path independent. It doesn't matter how you get from this distance to this distance. Any path will give you the same thing. So you could go from here to here, and then perpendicular to the field from here to anywhere. Well, you're moving perpendicular to the field, there's no force. Okay? So all that matters is going from here to here. Well, those things are kind of important to understand. Here, change in potential from A to B, it's just the field times the displacement. Displacement from A to B is B minus A. And then, of course, it's negative that because the change in potential energy is equal and opposite to the work done by the net charge, by the net force. Okay?